Good afternoon, everybody. Our project is about multiple vehicle detection and tracking using an adaptive method system. Team members are myself, Firas Quran, and Michael Giardino. All right, first we're going to talk about the abstract. Well, the research presents a technique for detecting multiple vehicles using a fixed single camera. And we use an improved medium-based method for generating the background image. And that image is compared to all other images for the background subtraction to identify moving objects. And after that, we also use the neural network to help aid with object detection and in the background subtracted image. And in addition to that, we also use multiple metrics to determine the best vehicle center. We use three ways. We use a similarity masking, the multivariate Gaussian distribution based on the velocity of the moving object, which is the vehicle. And we also use the Gaussian distribution based upon visual centers. What we do is we multiply all three of them together, and we determine the best choice of the vehicle center. And of course, we use a threshold to determine if it's a valid center or if it's not a valid center. If it is, it'll move to that valid center and track it. And if it's not, it'll be linear and linear in the expected direction. Well, see, the problem here is that it's really hard for human beings to track, to monitor many traffic cameras because it's almost everywhere in the world now, and it's too expensive for humans to hire humans for traffic monitoring. So the solution is to develop an inexpensive automated traffic monitoring system. And this system should be adaptive to weather conditions, it should be adaptive to the lighting conditions, and it shouldn't need like constant collaboration from humans. Our goals are to track every moving vehicle in the frame and to differentiate between vehicles and other moving objects such as trees, people on bikes, and etc. And the tracked vehicles should also be, if they're behind a tree, we should still have to track them and find them again once they reappear from behind the tree. Here are our topics. First, we're going to talk about the background image generation. What we did is we generated the image by computing the pixel-wise median sequence of the images. In our case, we took around 300 frames, and we got this background image, and that was compared with each frame to get the background subtraction image. Oh. I'm missing a video. Okay, missing one. Another topic is the neural network, elimination of noise. Over here, well, we use a neural network because it provides a more dynamic and more powerful way to calculate the size map. Meaning, as you see, there's a car right here, and the car right here is actually bigger than any other car up there. And we didn't have that data to provide it to the program. So what we did, we run in the MATLAB program, and it provided this data to us, and it was better for thresholding and identifying that it's a moving object, because before we had a problem, we couldn't really identify this one, but we could identify all the other ones. And we fixed that problem by improving our neural network. And here's the actual neural network image.
No, that's the...
So image subtraction.
That was the one that was supposed to be before, yeah.
Yeah.
Sorry about that.
And
That's
this is the actual neural. You can see it gradually darkens. The white one represents more of a bigger image, and it gradually decreases once it goes up there. You have a sharp...
What it's really doing is like function approximation for the size of the vehicles based upon data we gave it.
Mm-hmm.
I don't get it.
You don't get it?
I don't get that. What you're depicting.
I'm depicting, okay, anything in white. This is the actual image provided by the neural, after we ran the neural network. Anything over here, it finds that it's a bigger image. And once it keeps going up the street, let me show you, like, right here, there's a street. You see how it's bigger? Every time it moves up, it actually gets smaller. And it actually decreases every time it goes down in color. Intensity shows how big it is.
We also tried lots of different techniques for the neural network to try to get better images. There's a few others that we didn't put in, but we'll talk about that later. But, yeah.
And another topic is the visual centers, how to detect them. What we did first is we try to find first the edge of the moving object, and we did that by using horizontal and vertical filters. And after we found the edges, it's actually in the red around the object right here. After we did that, we took the maximum and minimum of the x and y coordinates, and we took the average of them, and we found the centers, which are in blue right here. This is another vehicle, it's a truck. Another one right here, and yeah, another one right there. And now I'm going to hand it off to Michael to explain.
And in order to identify vehicles, originally we used just a similarity, and we would this is a little math heavy, but basically what we're doing is we're subtracting from our search area. Let me get a picture of it. We're subtracting from our search area. We take a mask, and then this is our search area, and we subtract, do a pixel-wise subtraction through this entire search area, and the one with the largest, or the one with the smallest difference, we invert it, and it gives us a similarity. It's not exactly correlation because we're subtracting instead of multiplying it, but this is it's cycled through it's slid across the search area. And originally what we did in the previous semester was we would look for the point, and then if there were a visual center within it, we would just assume that the visual center was the right center. But now we decided to make it a little more nuanced and take other things into account, because there were some times when it would just find the closest center to the similarity. Like so say this is the point that's most similar, which makes sense. But then say there were a visual center here and here. It would choose the one that's closest, even though that's not necessarily. Maybe it was a car traveling in the opposite direction or whatever. So what we decided to do is, and also the other thing is before it was only doing black and white similarity. This time it's actually doing based on color, RGB color space. And I'm like flying back and forth between these slides. So if it has an identical match, the Euclidean distance will be 0. But then we use this function here to normalize the similarity. We just figured out that through looking at the data, a Euclidean distance of about 10 was seen to be a pretty good match. So we set that to equal about 0.75, and then just fit a decaying exponential function, which so if it's exactly the same, the distance is 0, which makes it a 1, and then as it gets smaller, as the distance gets larger, the function gets smaller and it becomes less similar.
How's that decreasing?
Oh, that's a negative. I think there's a negative there actually. Whoever did the slides did a terrible job. Yeah, sorry. That's a negative. It's a decreasing exponential, not a. Yeah. So anyway, like I said here, this example is from frame 237, and it was identified as a vehicle. So it takes a mask centered at it, and then this is the next frame. So it's searching for this vehicle, and this is the result of the similarity run through that function. But as you can see, like everybody else was talking about, very low resolution. I mean, this is supposed to be a vehicle, and I mean, if I didn't tell you it was a vehicle, you could think it was, anything at all. So it was a real challenge trying to get something that would work for vehicles that were so indistinguishable as vehicles. Two other things: we used the similarity, but then we also used a Gaussian based upon the velocity. So what we do is we take the previous velocity, called delta x, delta y, and then we find the angle that it's moving, and then we calculate 2 sigmas for the Gaussian function on the x and y, and then we do a Gaussian, but it's actually not. It's got a max value of 1. It's not over the divided by square root of 2 pi. But that's the Gaussian function, and that'll give. Here's a good example. This is that same vehicle in the same frame, and this is our. That's the mask area. This is the search area, and then this is the Gaussian velocity And I mean, you can see right at the end here, it starts to move in this direction, and that's why it's sort of curved this way, sort of. And then that's superimposed on that search area. Same. So then you have that data, and then you have this data also in the search area. So you multiply those two together, and then you also, from all these visual centers, as Faraz was talking about, where you edge detect and find the centers, then we placed Gaussians based upon the neural network size to determine whether a vehicle could be there. So then it'll center on, it'll take a mask of the search area, and then it'll multiply all these together, and then whatever has the highest value within the threshold, it'll move to that point and assume that that's an actual vehicle. There are two modes. Originally, it was a very important distinction, but now it's not so much, because before, if it couldn't find a visual center within the search area, it would just move linearly looking for another one. But now it's not as important, because it's always moving linearly to try to find its new spot for the search area, and then it uses all the metrics to find the best position. But we still call it linear mode when it doesn't meet the threshold, because we have to then eliminate permanently lost objects. So if something's occluded, either by running off the edge of the frame, or behind a tree and it never comes back, or whatever, eventually it starts to if you don't get rid of them, it just fills up, and you'll see towards the end of some of the frames, some of the videos, it just explodes with objects, because trees will wave, and then they'll disappear, and then so it'll try to track where it's going to be next, and then another tree will come up outside of it, and it just, so we had to start eliminating them if they weren't valid, and it's a lot harder than I thought it was going to be. So we had a few problems. The movement of the trees, they move actually a lot more than vehicles, and in very strange ways. So like I said, it'll start to move, and then it'll stop, but it'll keep looking for movement in that area. So it'll start moving off in this direction, and then it'll move again, and create a new vehicle. And so we eliminated the smaller objects by using the neural network, by deciding that something over here should be at least 40 pixels wide, so the little trees moving just a little bit wouldn't show up. And then also we eliminated objects that appeared for only a short time, because a lot of times it would just happen for a frame or two and then disappear. So that worked. We had we had many other problems too. The low resolution vehicles in the background. Like I said, it's actually really hard to see those vehicles in the very back. The cars in the front are 80 or 100 pixels wide, and the ones in the back are 7. So you can't even. A lot of the other research used models of cars. Like they were using IMAPs and comparing them. You couldn't even do that, because they're not even distinct. You can't even tell that it's a car. You can only tell that it's motion. Obviously we had World Cup problems, because middle of the day in South Africa, they could have picked a better time for us. But it's over now, and we have less than real-time processing speed too. So we removed edge detection in 3 colors, and instead of identifying each pixel size and doing different Gaussian blurs based on the size, we just split it up into regions, which was helpful. We have some videos to show that we actually did something. We're not just making all this up. Here that's a moving vehicle, and so you can see the tail. This is previous. The previous points of it, and you see this one's about to disappear, and then it starts to run off. It's moving in linear mode, and then it disappears.
Same thing with the trees right there.
Mm-hmm.
And the most important thing before, because of the neural network, we couldn't detect any vehicles coming from down there, but now we can. Like I think in the second issue, one of them should come out.
And you can see here, like the movement in this tree is as big as the car. And it's really hard to tell. We didn't pick an easy video to choose. I think we should have.
See, now it detects the big one right there.
Maybe got in a parking lot or something. I'm not really a fan of this video, actually. I mean, you know, even here, it's as large as these vehicles. So to eliminate a tree without eliminating all these other cars, it wasn't easy, and that's why you still have a lot of noise in here. But you can see down here that even this is an edge-detected blob, and there's some down here. But because of the neural network, there's one here. Because of the neural network, it doesn't detect a center there.
Should work much better in winter.
Yeah, actually, because the original video from last time was in winter, and I didn't even realize there was a tree right here because all the leaves are gone, and then you could actually see cars. Now you can't see anything. I mean, the only place you can really track a vehicle reliable is like right there, and I guess here. Yeah, we can go and see the other videos are really short. Huh? Yeah, go ahead. Well, that's good. Oh, there it is. Yeah, and that was it. And this is a little later on that used some of the other metrics. It's a really short video. I wish it would have. Can you pause it right there? And it uses this. See, as you can see, this looks more like the one that I showed you with the black and white. The frame, the masking area is a little bit bigger, and the search area is moved in the direction of the motion, which is like predicting where it's going to be. You don't have to show the other video; it's just the same, basically. And then there's a little bit on future work. We hadn't done any actually like quantitative evaluation of how it works, because I mean, who needs that kind of stuff? We'll just tell you that it works, and no, we really have to actually manually count cars and see how many it detects. We have to eliminate multiple objects centered in the same point. Sometimes it'll disappear, and then we're not exactly sure why it happens. Like you'll start to get multiple detected squares around the same object, and it's pretty easy to eliminate, but we don't really have like a cleanup function to go through and double check all this stuff.
Sometimes the car is actually split into two. It finds two centers. Sometimes.
Yeah, and then it'll start to track both of them. One of them, it'll come back together, and then it'll still be trying to find another one, and they'll jump.
What happens if a tree branch is right in the middle of the car, so it just splits.
Right, and then also trees will then find cars, and then you'll have like 4 or 5 vehicles tracked on the same vehicle. I mean, it looks all right, but it's not actually right. And then we need to do some kind of real-time evaluation, run it like overnight on some video, eliminating non-vehicle noise with the trees, using motion characteristics. I saw this paper that actually said that using this color space is actually a lot better for detecting vehicles. I don't really know why yet, but that would be an easy fix to see if it may change something. Shadow illumination, there's a lot of work on that, more in high resolution stuff. Improve motion prediction, and then some kind of rule-based prediction of where cars are going to go. Thank everybody for their help, and you have any questions?
How are you using color?
Just in similarity. It doesn't show in the pictures just because in order to show the edges. Where's the video? It doesn't show we're using color for the similarity. We're doing 3, 1 in each color for, where is it?
Right, you said
This is color sort of, but I mean, plus in the back it gets so washed out. There's not really a lot of contrast between colors, so you can't really see. But it did seem to help a little bit when we used, because this was just grayscale similarity, then it was color.
We tried using color for the whole thing, but it was too slow.
Yeah, he rewrote everything in like 3 colors, and it just like started crawling. You couldn't do anything with it. So, but and it wasn't really all that important for edge detection because it has always found outlines pretty well.
But it seems like it would be really easy to use it to eliminate the damn trees that are causing so much trouble.
I'd like to just eliminate all, not even use
Eliminate.
green
If
at
it's
all,
green,
but
no.
I'm afraid that a
There
tank
aren't
would
that
roll
many
down the
cars on
street,
the
and then we wouldn't see it. I mean, that's the one thing we're trying to find is our tanks, and there's no.
Right, okay.
Yeah.
Any other questions?
So do you consider to take this terrain condition or maybe road network into account when you track the vehicle? Maybe are there any previous work talking about that?
Using a neural network to track?
Yeah, well, I mean, to basically to model, to estimate the terrain condition, like
No,
where's the road, where's your camera?
There's not really that. It seems like everybody's using much higher resolution video, and so they're I mean, like I said, they're doing 3D models of the terrain. They're doing 3D models of cars to try to determine, you know. So there's not really a lot of work on using this, because we may have to switch from the neural network to just purely statistics based size estimation, because we can't get the neural network to do a nice.
Okay.
You know, maybe if we knew a little more about it, we could get a better approximation of the road and everything.
In your experiment, would the size of the vehicle matters, like a pickup or truck? Okay,
They're pretty close in size. They're within our thresholds of. It didn't make a big difference. Down. Let me find a picture of vehicles or something. Yeah, well, I guess this will work. I mean, here, this is a car would still have about the same footprint there as it would as a larger truck, and we didn't have an upper threshold of movement either,
Okay.
which
So meaning that if there's like a school bus coming by, you can still track.
it should still, yeah, it's the smaller things it has trouble with, because there's a floor to what about half of the expected size it won't track.
I see. So if someone riding the bicycle, probably you wouldn't recognize.
No, it wouldn't put a center on it, probably.
Okay.
Probably. If you were in the tree, though, swinging around, it would definitely find him and track him the entire time.
Tarzan.
Any other questions? All right. Well, thank you.